Electromagnetism, well, that's quite a word. We're connecting electricity, positive and negative charges, which we know something about, with magnetism, magnets, we'll learn something about those, and light, and trying to show how they're all connected. And we can start by noticing that magnets are kind of connected. They got a north pole and a south pole, which kind of reminds us of the positive and negative charges for electricity, especially because like poles repel and opposite poles attract. But if we look at the magnetic field lines, well, field lines, we got electric field lines. Magnetic field lines look different though. Think of them as magnetic field loops. Loops because you can never have an isolated north and south pole. And you think, yeah, I can just cut that magnet in half. Well, you could do that, but if you did, you would not get an isolated north and south pole. You can have an isolated negative charge. You can't have an isolated north or south pole. So that's the difference. Let's talk about how they're connected. A moving charge creates a magnetic field, and how better to move an electric charge than through a wire. Here we have a moving charge creating a magnetic field. We have our first right hand rule. Take your right thumb, point it to the left, and you'll notice if you curl your fingers that you're not really hitchhiking, you're kind of doing something here, but you'll notice that your fingers are pointing towards you. Your fingers are pointing towards you below the wire. That's what those dots mean. You see, we need 3 dimension here. So those dots, think of them as little eyeballs. They're looking at you. The magnetic field is pointing towards you below the wire. The magnetic field is going into the screen above the wire. It's kind of hard to twist your hand that far, but if you could, the magnetic field would be going into the screen above the wire. The first right-hand rule. But what if we bend that wire into a loop? Well, we'll have the same sort of thing. A moving charge creates a magnetic field, and here we'll have the magnetic field from that loop of wire, a second right-hand rule. Yikes. This one's a little bit different. This time you kind of are hitchhiking, and the fingers are for the current, and the thumb is for the magnetic field. We have a lot of right-hand rules here, but here we have a moving charge creating a magnetic field, and if one loop does this, many loops can create an electromagnet. A moving charge creating a magnetic field, and we're skipping over the equations. But you can kind of guess what those equations might be. For this wire here, we could say that the stronger the current, the greater the magnetic field, and the closer you are to the wire, the stronger the magnetic field. For this electromagnet, you could say the stronger the current, the stronger the magnetic field, and the more loops you have, that would make the field stronger too, and also a smaller radius would pack those field lines together closer. We're skipping over the equations though, but hey, look at this. This magnetic field here looks just like this magnetic field here. Kind of gives you a clue as to something happening inside this magnet. Anyway, if you have an electromagnet, you can create a doorbell. A doorbell! Here we close the switch and turn that coil of wire into an electromagnet, and then we accelerate that hammer towards the bell. The iron hammer is accelerated towards the bell, and it rings, and it's on a spring. And if you can create a doorbell, you can create a speaker. The speaker does the same thing. The electric current is a little bit more complicated now. It corresponds to your favorite song, but then you have a changing magnetic field, and you have an oscillating cone, an oscillating pressure wave, a sound wave corresponding to that electric signal, and it's all thanks to magnets. Did you know that there's a magnet inside your earbuds? There has to be. It's a speaker. There's a magnet, and you can use it to pick up a paperclip. Key point, a moving charge creates a magnetic field. Let's turn it around. A moving charge in a magnetic field feels a force. Well, when I say fields, you think force. So a moving charge in a magnetic field feels a force. And we have here another right-hand rule. Think about that positive charge. Take your right hand, take your right thumb, point it towards the screen. Point your fingers to the right. Notice that your palm is pointing down. So if you fire a positively charged particle into this magnetic field, and then the force is down, a negatively charged particle would have an upwards force on it. Notice you have to have the velocity perpendicular to the magnetic field lines in order for this to work. And somebody's thinking there, I see that force, and I see that current or that velocity. They are perpendicular to one another. Now, that reminds me of something. When the acceleration or the force is perpendicular to the velocity, circular motion. That's right, circular motion. Let's look at this positively charged particle at the bottom there. Pop quiz, tell me about that magnetic field. That's right, it's into the plane. So take your right thumb, point it to the right. Take your fingers, point it into the screen, and the force is up. But enough about throwing particles. Let's talk about wires. Again, a moving charge in a magnetic field feels a force. So we have this wire and the current in that direction and the magnetic field, and then the force comes shooting out of your palm. Not unlike Star Wars. Again, point your right thumb into the screen. Point your fingers to the right, and the force is down. A moving charge in a magnetic field feels a force, and if we reverse the direction of the current, the force is up. This time you have your thumb pointing away from the screen, fingers to the right, palm upwards, force is upwards. So I know what you're thinking. If we can have a downward force and an upward force, that could give us a torque. Bend that wire into a loop, and then you can have a torque. We can put a torque on that loop, and if you can put a torque on a loop, you can create a galvanometer. Galvanometer. What are you? Galvanometer. You can create an electric meter. See what we're doing there? The more current you have, the stronger the torque. The stronger the torque, the more that needle will bend that spring. And as wonderful as meters are, it'd be nice if we could change a letter or two and change that meter into a motor. How can you do that? Well, first you get rid of the spring, and we need to figure out a way to get this loop to turn and then this loop to turn again. And the way you do that is with those brushes. The way you do that is with something called the commutator, which changes the direction of the current. The details are important. We're glossing over them, just like the equations are important, and we're skipping over most of those too. But here we have a moving charge in a magnetic field feels a force. Electric motors are kind of heavy. Why are electric motors always kind of heavy? Well, they've got coils of wire, kind of heavy, and permanent magnets, kind of heavy also. So fact 1, a moving charge creates a magnetic field. Fact 2, a moving charge in a magnetic field feels a force. Fact number 3, cutting magnetic field lines creates a current. Cutting magnetic field lines. So again, the idea they have to cut the magnetic field lines. We've seen that before. New right-hand rule. Take your right thumb. That's the direction of the velocity. Your fingers, that's the magnetic field. And then current shoots out of your palm. Again, not unlike Star Wars. And this is kind of a half law. This is kind of a half law because you can't really have just this current going upwards in this wire. I mean, in order to be a circuit, it has to be a complete loop, so it'd be weird to have this infinitely long wire with a car. I've seen it in a physics problem, but never in real life would you have just an infinitely long wire with a current in it. We're talking about loops of wire, and that means a changing magnetic flux creates a current. A changing magnetic flux, well, what's a magnetic flux? Think of it as the number of field lines in that loop, So here we have a guy throwing a magnet at a coil of wire. Kind of a strange thing to do, but if you did, you'd measure a current. With that electrometer that we talked about before, you'd measure a current in that loop of wire. As long as you had a changing magnetic flux, as long as the number of field lines was changing. Let's look at it this way. A loop of wire in a magnetic field. And how can we change the number of magnetic field lines that are going through that loop of wire? Rotate it. Rotate it quickly and you'll have a bunch of field lines cut. You'll have a changing magnetic flux, a changing number of field lines through that loop of wire, and you will induce a current. A changing magnetic flux creates a current. That's one way. That's a good way to have a changing magnetic flux. Here's another way. Take that loop of wire and leave the loop of wire alone, but change the magnetic field. Change the magnetic field, you'll change the magnetic flux. And how can you quickly change a magnetic field? With an electromagnet. Here this guy is flipping that switch, starting an electromagnet, changing the magnetic flux through that secondary coil, and he will measure a current in that secondary coil. Kind of like this, same sort of situation. A coil on the left, hooked up to a battery. A coil on the right, hooked up to a meter. And initially, nothing is happening. But then you throw the switch, and you get a blip. You throw the switch on the left, and you get a blip on the right. Again, why just a blip? Because a changing magnetic flux creates a current. When that switch is closed, you have a changing current and a changing magnetic field. And that changing magnetic field creates a current. But once the switch has been closed for a while, nothing much is happening. You might have a magnetic field. You might have a really strong or really impressive magnetic field, but if it's not changing, it's not doing anything for that coil on the right. And this reminds me of something. This reminds me of that elevator situation where when you get into an elevator and you stand on a scale and the elevator accelerates upwards, then you have a changing reading on the scale. But once you reach your cruising upwards constant velocity, then the scale goes back to the natural weight, the normal weight. So if you remember that. Anyway, the point I'm trying to say is that a changing magnetic flux creates a current. And then when you open the switch, you get another blip. When you open the switch, you get another blip. Once again, you went from a magnetic field to no magnetic field, so that's going to be a changing magnetic field, which will create a blip in the opposite direction, again kind of like the elevator, and a changing magnetic flux creates a current, and we have a left-hand rule. When the change in magnetic flux increases in the direction of the left thumb, the induced current follows the fingers around in that loop there. And if we can create a current, we can create a generator. Here we have a person turning a crank or some other energy source turning that crank, and a changing magnetic flux. Hey, look, a coil of wire. As it rotates, you'll have a changing magnetic flux creating a current, and that makes us happy because we have generators and motors. And this makes us happy because of energy. We're thinking about energy here. If you can turn mechanical energy into electrical energy with a generator on the bottom there, you should also be able to turn electrical energy back into mechanical energy with the motor. You could hook one of these things up to another and get absolutely nowhere. But we're trying to get somewhere. We're trying to connect electricity, magnetism, and light. Again, we've said that a moving charge creates a magnetic field. Check. We've said that a moving charge in a magnetic field feels a force. Check. We've said that cutting magnetic field lines creates a current, which means that a changing magnetic flux creates a current. And they work together, but they also kind of work against each other. Here's an electric generator. It doesn't look like a normal electric generator, but it gets the point across. Let's take that bar in the center and move it to the right. A bar in the center moving to the right, and that will induce a current. Again, tell me about the magnetic field. Those X's mean the magnetic field is into the screen. So take your right thumb, point it to the right, twinkle your fingers towards the screen, and the current goes up. The current is going up in this diagram, which is wonderful because you induced a current and everybody's happy for you, but there's a problem. There's a problem. Do you see what the problem is? The problem is the other right-hand rule. If you have a current, an upwards current, point your right thumb upwards. If you have an upwards current in a magnetic field, right thumb up, fingers twinkling towards the screen again, then you will feel a force to the left. Electricity and magnetism fighting against each other, which is disturbing, but also kind of makes a little bit of sense. I mean, you can't generate an electric current for nothing. Grease up those tracks, throw that wire to the right in the magnetic field of the Earth, and you could conceivably have an electric generator that didn't cost you anything. But you can't because of that force that comes from electricity and magnetism fighting against each other. Or think of it a different way. Think about it in terms of magnetic flux. The number of field lines into the page is increasing. So take your left thumb and point it at the screen. Then your left fingers curl in that direction. We are making a loop of current. A loop of current. Oh no, I've heard about that. Take your right hand and make that circle with your right fingers, and then your thumb is pointing at your nose. Your thumb is pointing away from the screen. Again, I know the details are confusing, but we'll see here again that there is an opposition here. An opposition at the heart of electromagnetism. Electricity and magnetism are fighting against each other. Not only did that bar moving to the right encounter a self-made resistance force, but here we have the current is creating a magnetic field that fights against the magnetic field that made the current. We're fighting against each other. And the term for that is light. Light, an electromagnetic wave. The changing electric field creates a magnetic field, and the changing magnetic field creates an electric field, and they go on forever. We'll leave that for the next part.